This is a second-order circuit exercise. In the circuit in figure 4 below this circuit, all resistances are given in ohms. The switch, this one, has been in position B for a very long time, so it's in steady state. The source is DC, it is in DC steady state. At t equals 0, the switch is moved from B to A. Find what is this current. This one, the current in the 0.5 ohm resistor. Find the value of that current at 0 plus, the value of its first derivative with time at 0 plus, and find for t greater than 0 that current as a function of time. The first thing we do is to take a snapshot of the circuit at t equals 0 minus, that is, right before we move the switch. The circuit is in DC steady state, so the capacitor is represented by an open circuit and the inductor with a short circuit. From this snapshot, we immediately realize that the voltage in the capacitor, VC0, is the value of the source, 4 volts, and the current in the inductor, IL0, is 0. Now we take a snapshot of the circuit at t equals 0 plus, that is, right after we move the switch. The capacitor is represented with a V source with this value, and the inductor with a current source with this value, but a current source with 0 amps is equivalent to an open circuit. The initial value of the current in the capacitor is negative 4 divided 0.5, negative 8 amps. This implies that the derivative of the voltage in the capacitor at 0 plus is equal to that value divided by the capacitance of 1 farad. However, the initial conditions we're looking for are not in the capacitor or the inductor, but on this resistor according to the exercise. So let's see what is the relationship of that current and the voltage in the capacitor and the current in the inductor. Let's make a drawing of the circuit for any point in time t greater than 0 by considering as unknowns the voltage in the capacitor and the current in the inductor. In this generic circuit for any point in time after we move the switch, the capacitor's voltage is unknown, so I have represented that with a generic V source with an unknown value Vc of t. And the current in the inductor is also unknown, and I have represented it with an unknown current source with the value IL of t. What I want is to write this current, our unknown current, as a function of Vc and IL, or at least one of them. The solution in this case is simple. That current is Vc of t divided by 0.5, like this. And this is valid for any point in time after we move the switch. Which means that if we know the initial voltage in the capacitor, which we do, we can determine the initial current in the resistor, so this current. The initial current is 8 amps. And if we differentiate this expression, like so, this expression is also valid at any point in time, in particular at 0 plus. That is 2 times that multiplies negative 8. And these two are the answers to part A of the exercise. Now we write the differential equation for part B. For t greater than 0, I have replaced inductor and capacitor by the P impedances. This circuit needs a fake source. I will use this fake current source in here. If you don't know what they are, please watch the video on utilization of fake sources in solution of circuits with no sources at all. Reference node, node 1, 1 KCL equation, current in the capacitor, current in the resistor, current in the inductor. From there we solve for V1, like so, which is a second order differential equation. But what we're interested in is this current, not that voltage. So that current is just the voltage divided by this resistance. That is, this divided by 1/2. That current we're looking for is this divided by 1/2. This is the differential equation we're looking for. Now, that fake source has a value of 0. So this is 0. And the differential equation we're looking for is the eigenvalues of this differential equation are complex conjugate with this sigma and this omega. That current has this form: K1 e to the negative t sine 1732t plus K2. The final value of that current is evidently 0. So that is all the expression. We need to find K1 and K2, and for that we have the initial value of this current, and we have the initial value of its first derivative. If we utilize those as in class, just see the class notes, we obtain that the current in that resistor is negative 9.238 sine of 1732t minus 1.043 radians amps. And that is the solution to this exercise. Thank you very much.